Hi everyone, welcome to this video. Today I'm going to show you how this Python project works. This is a project related to the data analyst field, and today we're going to check this file. This is the Nanotox dataset. This is a CSV file, and this is a dataset that I obtained from this website. So let's check this website. I'm going to show you where did I get the file. This is the Kaggle website, and here we have the Nanotox dataset. So this file contains data about nanoparticles. I have built this code. I'm going to do a walkthrough of the code so that you will know how this program works. First of all, we import the proper libraries. We're working with pandas, and we are working with matplotlib, and we are using pandas as PD and matplotlib as PLT. We are also using import O's so that we can create the graphs folder just in case it doesn't exist on the workspace. In my case, I just deleted the graphs folder, so this will be useful to create the graphs folder again once we are creating the files for the different graphs that we are going to create in this project. This is a graphs folder. So first of all, we are reading the CSV file. So in this try, we're going to look for the CSV file. This is the name of the CSV file that we have at the root of the project. So if the CS file is properly loaded, this print will appear on my console, and also the available columns will appear on the console. What are these available columns? The names of the columns that we have here. The MPS, the core size, the idle size, and all that. So this os dot make dirs is to make a directory, is to create the graphs folder just in case it doesn't exist. Here I declare some variables. These variables are going to be useful to get the proper column. As you can see here, MPS is for the nanoparticles types. Core size is the nanoparticle size. So this is my variable. And surf area is for the area of the nanoparticle. So I write that variable down. So these are the names of the columns, and I'm just using them as a variable here on my Python code. These are some variables to remove missing values and to get only the data that has valid numbers. And here, I mean, here above with the df, this means data frame. I'm reading the whole CSV file, yeah. But here I'm cleaning the CSV file to obtain only the values that I want. So here I'm obtaining the number for the nanoparticles that are toxic, and I'm obtaining which the amount of nanoparticles that are toxic for each type of nanoparticle. And here I'm transforming that number to a percentage, and below I'm using the same df clean function, I can say, to obtain just a small amount of the data set. For example, here I'm obtaining the data set for aluminum oxide nanoparticles and the instance where the nanoparticles are toxic. Here I'm obtaining the data set for copper oxide nanoparticles, and only in the case they are toxic. And I'm doing the same here for iron oxide nanoparticles, for titanium oxide nanoparticles, and for zinc oxide nanoparticles. And here below, I'm making two personalized subsets of data to get the data for copper oxide nanoparticles, to titanium oxide and zinc oxide nanoparticles, in the case they are toxic and in the case they are toxic. Later on, we will use all these variables that we built here. Uh, here I have a group the stats variable. This is to read the clean data set, and grouping by nanoparticle type, we are getting all this information. What we are getting the average size, that is the diameter of the nanoparticle. We're getting the surface area, we're getting the superficial charge, and we are also getting the sample count, and we are also getting which nanoparticles of this sample are toxic. So this is something that is going to be displayed in my terminal. Here I have a print to print the group the stats that we have here. And here below we have a similar group of stats, but this is just for the toxic nanoparticles, and this is just for the non-toxic nanoparticles. Here we have the code for the first graph. The first graph is a graph that allows us to see the count of toxic nanoparticles and non-toxic nanoparticles for each nanoparticle type. So here I have the description, the framing of the plot of the graph. I'm telling the code that I want a bar graph. I'm telling which colors I want to be used. I'm telling which color I want the edge to be. And I'm telling what size the bar plot must be. Here I'm writing the title for the bar graph. Here I'm writing the Y level, and here I'm writing the X level. This legend is used to have a square where the colors of each side of the bar are displayed. So a color will be for non-toxic nanoparticles and another color will be for toxic nanoparticles. Here I'm telling the program how I want this file to be saved. I want this file to be saved as a PNG file, and this is going to be in the graphs folder, and this is going to be the name of the bar plot. Once I wrote all the titles and specifications for this bar plot, I write a plt.close, and then the file will be created. All the other charts and graphs and scatter plots that are on this project are written following the same structure with some additions according to the case, but all have the same structure. So if you don't have this extension installed in your VS Code, you won't have this play button that I have in the upper right corner of the screen. If you press this button here, the Python file will start to work. All right, it already did the work it was intended to do. We have this message here that says the Nanotox dataset CSV file was successfully loaded. This means that the file that we declared here was actually there, and that Python was able to read what was inside the file. Here we have the available columns. The available columns were intended to be printed here, and here we have them. We have all the columns just as they are in the data set in the CSV file. Here we have them. And we also got the grouped stats that were intended to be written here. We have the aluminum oxide nanoparticles, the copper oxide nanoparticles, the iron oxide nanoparticles, the titanium oxide nanoparticles, and the zinc oxide nanoparticles. We have the average sizes for each nanoparticle type, the standard deviation for each one of them, and we have the same columns for the surface area and the surface charge. We also have the sample count. We can see here that there's a greater number of zinc oxide nanoparticles than there is of any other type of nanoparticles in this data set. There was only 18 aluminum oxide nanoparticles or samples considered for this project. We can see here that there were only 18 samples of aluminum oxide nanoparticles. This 18 is for the samples of the nanoparticles, because in a solution of nanoparticles there are millions and millions and millions of nanoparticles. So these ones are the samples. In this data set, we are not told which synthesis method was used to obtain each type of nanoparticles, but we are told how many samples were considered for the data set. So we have 51 samples for copper oxide nanoparticles, 18 samples for iron oxide nanoparticles, 200 samples for titanium oxide nanoparticles, and 594 samples for zinc oxide nanoparticles. And here we have the toxicity count. If we go to the graphs folder that was created just a while ago, we will see that we have all these PNG files. We're going to start with this one. And here we have the count of toxic versus non-toxic nanoparticles by type. Here we have all the labels and even the legend that we described before. I'm going to go to the code of this specific graph. Here we have the colors of the bars, count of toxic versus non-toxic nanoparticles by type. Here we have the title, the labels, the proper labels are written, and the file was saved as zero toxicity counts bar. We can see that the blue side of the bar are for non-toxic nanoparticles, and the red side of the bar are for toxic nanoparticles. We can see that the greater amount of samples of nanoparticles in this data set were for zinc oxide nanoparticles, and that among this greater sample, we have a great percentage of toxic nanoparticles. The next graph is another bar graph, and here I depicted the percentages. This is a 0 to 100% bar, yeah, but this is for each type of nanoparticle. So inside of the copper oxide nanoparticles, we have a 78.43% of nanoparticles that are toxic. Inside the titanium oxide samples, we have a 3% of toxic nanoparticles, and inside the samples of the zinc oxide nanoparticles, we have a 72.39% of toxic nanoparticles. So the data that we are visualizing in these first two graphs is enough to answer question one. Question one in this project is, among all the nanoparticles of the data set, which ones are toxic and which ones are not? In the website where the data set was obtained, there was no instruction or detail about what toxicity meant. We just know that there are some nanoparticles in this data set that are toxic and some nanoparticles that are not. but we are not told what toxicity is. We are not told where these nanoparticles are used. We are not told if they were used in humans. We are not told if they were toxic for the skin or the heart or the liver or the kidney, or we really don't know what toxicity is meant for this analysis. Going on with the rest of the graphs, we can see here an average core size by nanoparticle types. So here we have all the bars from aluminum oxide to zinc oxide nanoparticles. And here we have the proper error bars for each instance. The error bars were set on this graph by this GR function. So we get the plot data that comes from the group stats. And here we get the standard deviation from this STD size variable. The STD size variable belongs to the group the stats. Here we have the STD size variable. And here by writing STD, we are telling Python to calculate the standard deviation of the nanoparticle size. So going back to the graph, we can see that all the nanoparticles are below 100 nanometers. Nanoparticles are particles which have a diameter that is below 100 nanometers. So if we have a particle in a solution, in a chemical solution that has a diameter above 100 nanometers, it can be considered as a nanoparticle in a strict sense. So we can see that even with the error bars, all the nanoparticles of this data set are below 100 nanometers. In the next graph, we have the average surface area by nanoparticle types. Here is depicted the surface area in square meters per gram of nanoparticles. And we see here that we are also getting the error bars, and we can see the differences in surface area between each type of nanoparticle. The same can be said by the superficial charge. This is measured in millivolts, so it can have negative values, also positive values. We see here that aluminum oxide and copper oxide and even zinc oxide nanoparticles have superficial charge that is mostly positive. But we can see the contrary from the iron oxide nanoparticles and the titanium oxide nanoparticles that have superficial charge below 0. So this is a negative superficial charge. Here we have some scatter plots. These scatter plots were made to find relationships between the variables of the nanoparticles, and they were made for each type of nanoparticle. So here we have the core size versus surface area of aluminum oxide, copper oxide, iron oxide, titanium oxide, and also zinc oxide nanoparticles. And these scatter plots were made only for the toxic ones. So here I have the code for the 5 scatter plots that compare core size versus surface area. Here we have 1, 2, 3, 4, and 5. And below we have the scatter plots that compare surface charge versus surface area. How do I get this information? Here I get a personalized data set that was the data set that only gets the information from aluminum oxide, and that only gets the aluminum oxide nanoparticles that are toxic. I created a personalized subset for each type of nanoparticles. Here we have the one for copper oxide nanoparticles, for iron oxide, for titanium oxide, and for zinc oxide. So we are getting the same data, but for a different type of nanoparticle. So with these plots, we can answer the second question. The second question of this project is there a relationship between the properties of the nanoparticles? And the answer is yes. At least for copper oxide nanoparticles and zinc oxide nanoparticles, where for a core size below 16 nanometers, the surface area began to increase from 20 to 80 square meters for gram. So this is something that is true and logic if we consider the materials science knowledge. When you get a smaller nanoparticle, the specific surface area of that nanoparticle will be greater. Now we are going to see the box plots. The box plots are statistical tools that are used to observe distributions in properties and in populations. So here we have the distribution of core sizes by toxicity. Here we have the distribution for the nanoparticles that are toxic and the distribution for the nanoparticles that are non-toxic. We can see the same in the next box plots, but for a different property. Here we are evaluating core sizes. Here we are evaluating the surface area, and here we have the particle charge. So we can see that toxic nanoparticles have greater diameters than the ones that are non-toxic. So this might be a property that is related to the toxicity of the nanoparticles. That if we have greater nanoparticles, it means that they are aggregating and that they are experiencing reactions that were not planned by the scientists that made these nanoparticles. As we saw before, a lower core size is related to a higher surface area. In this box plot, we can see that toxic nanoparticles are related to a higher core size. And here we can see that toxic nanoparticles are also related to a lower surface area, which has sense and is logic. And the last box plot is for the particle charge. We can see that the non-toxic nanoparticles have a span of charge that is more concentrated. The most of the non-toxic nanoparticles have a very stable value for superficial charge. Meanwhile, the toxic nanoparticles have show different results. They have a larger span of superficial charge, which might be related to why they are toxic, that they are not stable, so they have a distribution of particle charge that is very large, is unpredictable. And now to get done with the analysis, I'm going to take these subsets. As we saw before, only copper oxide, titanium oxide, and zinc oxide nanoparticles were the ones that were toxic. So I printed these additional bar plots to compare the properties of non-toxic versus toxic. So to answer the third question, which properties are related to toxicity? We can see that the properties that were related were a greater core size, a smaller surface area, and a change in surface charge that goes from negative to positive. According to all the data and all the graphs that we manage in this data analysis project, we can reach these conclusions. That is pretty much everything we can see by analyzing this data set. All the code that was used to produce the scatter plots and the bar plots and the box plots follows almost the same structure as I told you before. The only thing that changes is where we get the where we get the information from. Here we are getting this information from the non-toxic group stats, and in this other instance, we're getting the information from the toxic group stats, and we are retrieving different variables, different columns from the data set in order for the plot to be created. If you want to know more about how this project was built and other details that were not mentioned on this video, you are welcome to read the README file. I have here an overview of the project. Here I have the answer to the questions that were proposed for the data analysis. Here I have the description of the development environment that was used for this project. And here I have useful websites. Thanks for watching, and I hope you have a marvelous day.